Okay, hi everybody, and I am glad to have here Álvaro del Pino from Utrecht University that is going to bridge communities together today talking about billiards in subriemannian geometry. So I'm really looking forward, and the stage is yours.
Yeah, thanks a lot, Marcello, thanks, Marcello, for forcing me to talk about this. So I was a bit hesitant to talk about this paper. It's a paper joined with Lucas Dahinden from Heidelberg. And the point is, neither of us is a billiard person nor a subriemannian person, although we try our best. So yeah, basically the point is, probably many of you know about either of these topics much more than we do. So I'm kind of looking forward to getting like your questions and your input. And basically just, I cannot see the chat. So if you want to write your question, I guess someone will read it. But if you just want to unmute yourself and ask me, just do that. So, okay, so what's the plan? I'm going to introduce what subriemannian geometry is, and that's going to take a big chunk of the talk, actually. Then I will introduce the billiard problem, and I will discuss some concrete examples of tables in the setting. And the point is that this will allow us to see some interesting properties and some things you can ask. Okay, so what do we want to study? So what we want to study are the following. They are pairs consisting of a smooth manifold and a distribution. A distribution is nothing but a vector subbundle of the tangent bundle. So this means that at every point in my manifold, I'm choosing like some sort of subset of directions that I like. And the idea that, like the physical way that you may think about this is that M is some sort of configuration space for a particle. So you can think that, okay, in M, there's a particle moving around. And this particle is not allowed to move in every direction. It's only allowed to use the directions in psi. So somehow psi consists of the allowed directions of motion. Okay. Now, it may happen, for instance, I could choose psi to be just 0 at every point, and that would be too restrictive, right? Because then I would be making my particle stay still. And of course, you could do less dramatic things and choose psi to be some other constraint. But let's say a constraint is strong enough that you forced your particle to live in a submanifold of M, right? So somehow you've restricted too much your motion. So I don't want that. I want my particles to be allowed to move in M kind of from any point to any other point. So maybe let me give you an example. So what is this? So this is an example. So I have 3 directions, right? X, Y, and Z. But I only like 2 of them. I like partial Y, and I like partial X minus Y to Z and combinations of them. Okay. So in the picture, partial Y is the direction that runs along these lines. And partial X minus Y dz is this complement, right? It's kind of here, it's flat, it's partial X, but as I move in Y, it starts turning. Okay, so I have 2 directions, and one of them turns with respect to the other one. And this is actually what this particle is exploiting to go up. So going up is not allowed. Sort of partial Z is not one of my admissible directions. But what happens is that if I want to move up, what I do is I'm the little particle, and I observe, oh, if I move a bit in Y, then the planes have a bit of a slope. So then I can exploit this slope to go up, and then I adjust to go again over the original point. Okay. So basically, let's formalize this a bit. So what I'm saying is, even though partial Z is not an allowed direction of motion, I can ultimately move along that direction by combining the directions that I have. And the way to say this is that these 2 vector fields, their commutator, their Lie bracket is partial Z. So this is kind of an infinitesimal phenomenon, right? But this means that by definition of the Lie bracket, really, that if I take the commutator of flows along partial Y and along the other vector field, then I describe these squares that go up. So that says that the commutator of flows moves along the direction of the Lie bracket up to 2nd order, and then there's sort of higher order noise. Okay, I hope everyone is happy with this picture. Just to emphasize, so this is what we don't want. Basically, what I don't want are foliations or things like this, right? So here we have the typical foliation by level sets, horizontal level sets in R3. The allowed directions of motion are partial X and partial Y, which they commute. And therefore, my particle is constrained to live in level sets. It cannot jump from one level set to another one. Okay, so this is what we don't want. I want the previous picture. And now I'm going to stop sharing, and I'm going to share but differently because I want to write things and I cannot do it like this. So share screen. Are there any questions? Okay. So, okay, hopefully now you can see me right. I'm gonna move everyone's faces to the other side of my screen. Okay, so here's the definition. So what I want to study are distributions where the distribution is so-called bracket generated. And what does this mean? So this means that I consider vector fields, let's call them, I don't know, x, y, z. There's some collection of vector fields tangent to psi. And now what I can do is, out of all the vector fields in psi, I can start taking brackets. And I'm allowed to take like kind of iterated brackets. So I could do something like this, and then I bracket it with z, and maybe I bracket it once more with x. I just take kind of all the brackets. And with this, I'm producing extra vector fields, and now I can do linear combinations of them. And what I want is that I get all of the vector fields. So what this kind of says is that kind of by infinitesimal combinations of my vector fields, I generate every direction. And therefore, I can move also globally. I'm kind of saying that because I can move infinitesimally in every direction, globally, I can also move in every direction, which is what I want. Maybe a fancy way of saying this, if you prefer this, and I do, is that the sections of psi generate all the vector fields as a Lie algebra. So this is kind of the opposite of involutivity, or the opposite of being a Lie subalgebra. Okay, so this is what we want. And okay, there's a few examples here. So I mean, my mechanical or physical motivation from before is what it's called like the basics of non-holonomic mechanics. So for instance, the example we just saw basically models a coin rolling on the plane. But there's many more examples, of course. This also appears in PDEs. So yeah, let me not spend too much time here. What I'm saying is, if you take a framing of the distribution, then you can kind of differentiate twice along such a framing. This is some sort of like Laplacian looking object, but it's not a Laplacian because it's sort of not differentiating against all directions. It's not elliptic, but it still behaves quite nicely. For instance, if the manifold is compact, this is a still Fredholm, and you can compute the index, something like this. This type of objects also appear in many other areas in geometry. So for instance, in complex geometry, if you look at some manifolds of complex manifolds, then they're complex tangencies. So basically you take this a manifold, let's say here it says 3 inside C2. You take the tangent space, you intersect it with the tangent space twisted by I. This will give you a subset of the directions. And now it turns out that properties of this manifold within the complex space are related to how the distribution behaves. And kind of for a similar reason, distributions also appear as the natural boundary structure at the boundary of symplectic manifolds. But okay, let's move on to the point of the talk. So we have manifolds, and at every point I've chosen some directions I like. Now the point is, since I can move between any 2 points, right? So I can move from any P to any Q. The question is, what if I put some notion of cost, and I try to minimize the cost among all possible paths that go from P to Q? So the way in which I formalize cost is by saying I get a metric, but it's a metric only along psi. Okay, so somehow like all the directions not in psi. So if V does not belong to psi, then it has infinite length, let's say. So they are penalized. So such a triple M psi with the metric along psi, we call it a sub-Riemannian structure. And what you can observe is that much like in Riemannian geometry, your Riemannian manifold is a metric space. The same is true here, and the picture is exactly what I do. So you have P and Q, right? And what is the distance between P and Q? Well, you take all the paths and you infimize their lengths. And of course, in this infimization, sort of the paths that matter are the paths that are tangent to the good directions, because all others are infinitely penalized, as I said. So you're just infimizing over paths tangent to the distribution. And from this perspective, what you can think is that M psi G as a metric space is kind of like a degenerate limit of Riemannian metric spaces, where kind of like the complementary directions not in psi, they are being penalized infinitely much. So you can think that, I mean, for every sub-Riemannian structure, you can find a sequence of Riemannian structures that metrically converges. Okay, so this is the setup. Are there any questions up to this point? Okay. Then, okay, let's do dynamics. So now we've introduced the notion of cost. So now we can do proper dynamics in the setup. And kind of the question is like, what are length minimizers, or yeah, what are geodesics? And let's make some remarks. So a sub-Riemannian structure or sub-Riemannian manifold is what you call a path metric space. So this means that it's not an arbitrary metric space. It's a metric space where, as we said, the distance between points is given by this infimization process over paths. So somehow paths realize the metric. So it turns out that Hopf-Rinow applies to such spaces. And if, well, okay, assuming M is complete, which I didn't write, but you should, of course, always assume for these things, then a minimizer between 2 points always exists. Okay, so, okay, first is check. So we have minimizers. Now, the point, of course, is that in Riemannian geometry, it's not that you have minimizers, it's that minimizers are pretty nice, right? So for instance, if I'm at a point, okay, if I'm at a point and I draw its tangent space, then what are the geodesics starting at P? So let's say unit geodesics. So unit geodesics starting at P are in correspondence with the sphere, right? With the unit sphere of the metric, right? So once I choose a vector here, there's a corresponding unique geodesic that sprays out of it. So what we would want to say somehow is that in the sub-Riemannian case, is it the same? Do we have a nice picture where we can describe the geodesics out of a point in a nice way? And the first remark is that, I mean, this cannot literally look the same as in the Riemannian case. And why is this? So let me do the picture again. So here I have P. Oops, I'm just not very good at drawing lines, sorry. So here I have TPM. Let's say here I have some subset which is psi at P. And now I fix a vector. And now the point is, okay, let's say I had like a similar picture in the sense that for every vector in psi, I get a unique geodesic. Look. Then this looks pretty bad, right? Because then it means that if I had a single geodesic per direction, then you would see like out of the point, you would see like kind of like a spray that looks like psi itself. But the point is psi, by assumption, this is smaller than the manifold. So if I want to be able to connect to all points nearby, the geodesic spray cannot look like this. So what this is telling us is that for every direction in psi, I must have more than one geodesic. And just dimension counting, it tells you that if you want to be able to go to connect to any point locally, at the very least, for every direction in psi, you should have a subspace of geodesics of dimension per rank of psi. Okay, so let's try to see how this works in an example, because then you'll see the picture much better, I think. Okay, so here's an example that is going to keep reappearing during the talk like a lot. So this is actually the same example as before. So this is the standard structure in R3 as appeared in the previous animation. But the point is that I've made a little change of coordinates. And the reason for that is that it's a bit more convenient later on for me. So the only observation to be made here is that here I have the, let's say, the radial vector field, right? This goes like kind of far away here. And then I have the angular vector field, let's say like this. And what you can see is that the angular vector field is really rotating along with respect to the radial one. And that says that the Lie bracket is non-zero. So that's exactly what we saw before. Okay. So let me make a little remark before we move to the next slide. So this structure is vertically invariant. And also rotationally invariant. And more important for the next slide, it's never vertical. Okay, So never vertical means that, okay, these planes, okay, they get more slopey as I go to infinity, but they never become truly vertical. So this implies that they always project nicely to R2. So the way we think about this is that psi standard, you can think of it as a connection in the bundle R3 over R2, where R2 are the x and y coordinates. Yeah. So because this projects nicely, this means that every direction in R2 lifts uniquely to each point upstairs. Okay. This will be important for manipulations I'm going to do next. So, okay. So this is what it's written exactly here. It says, okay, project R3 to the R2 that is horizontal. And now what we see is that the framing, the typical framing in R2, partial x, partial y, it lifts to a framing upstairs. That is, well, partial x plus some vertical noise, partial y plus some vertical noise. And now what is nice, of course, is that, I mean, partial x, partial y is an orthonormal frame for the standard planar metric. So what I can do is just lift the planar metric up. So what I'm saying is that I make these two vectors, I turn them into orthonormal bases of the plane. Okay. So I'm saying I'm defining the standard subriemannian structure in R3 to be just the pullback by pi of the planar metric. Okay. So now let me do a little picture, because this is what we're gonna play, the game we're gonna play next. So what we're saying is, if here I have R2, and here I have some planar curve. Okay, no. Then the following is true. Once I fix a lift for the first point, there exists a unique curve upstairs that projects to nu, and this tangent to the connection. Okay. So how do these two curves interact? So this is tangent, let's say, such that gamma prime belongs to psi. Right? Yeah. So yeah, curves lift uniquely to connections, is what I'm saying. And the point is that, I mean, so you recover nu from gamma by projecting, of course. And what we're saying is that you recover gamma from nu by lifting. And the length of gamma by construction is the length of nu, because the metric is just the lift metric. Okay. So, okay, let's see. Let's explain this a bit more. So what I'm saying again is I have some curve upstairs. It has three coordinates, x, y, and z. Now I define the projection nu that consists only of x and y. And what we're saying is that out of x and y, I can recover z by just integrating using this one form. Yeah. So this is the lifting process. This is lifting to the connection. So, okay, this is what this says. Gamma is recovered uniquely from its projection. And now let's get to the point. So where I'm heading with this is that what I want to do in this example is I want to compute what the geodesics were, right? And the point is that finding a geodesic between 0 and some other point is the same as saying, okay, I want to connect 0 to with xy, subject to the constraint that the final height is recovered from integration from the projection. And now let me explain a bit this parentheses briefly. So in the case where nu is closed, let me do this picture. So let's say nu is a closed curve. Then it turns out that this one form that I'm integrating, right? This is like a line integral that I'm integrating over nu. By Stokes' theorem, it's the same as integrating the corresponding two form. This is a potential for the classical area form in the plane. So what this says is, for instance, if I want z to be 0, so if I want my curve upstairs to close up, then the bounded area must be 0. So for instance, in this picture, this means that this area A, this is A, and this is minus A. The total signed area has to be 0 if I want to close. Okay, so let's recap. We are looking at curves that go from 0 to the desired endpoint. they also end up with the desired height. And additionally, I want to minimize how long they are. Yeah, this is the same problem, but now it's a planar problem. And what is nice, of course, is that basically I mean, it's a variational problem, but with a constraint. Right, so this is basically a problem of Lagrange multipliers, maybe. Okay, so let's get to the punchline. So the answer is, okay, what are the minimizers out of this description? And what you can observe.
Can I ask a question?
Of course.
I'm not really sure I understand how this area constraint works, because if you say that that you had the A and then one part had to be A and then the other part had to be minus A, so the total has to be 0.
Yes.
But what if I what if I have only a square? Like in gamma is the parallel transport idea, which you
yeah. So maybe let me do. So you want not to have 2 components, but to have a single one like this?
Yes.
So that's exactly what I mean. So what you're proving is any curve that projects like this, it bounds positive area. And therefore its lift, what it must do is this. So the area here is A, and the vertical displacement will be A. So that's literally what you're proving. So somehow a curve that doesn't have more than 1 component can never be closed upstairs.
All right, cool. Thank you.
Yeah, it was awesome. Yeah, thank you for the question. Actually, this will show up in a minute. So thanks. All right, so maybe we're happier after this question. Hopefully. So let's see. So what is the punchline? As I was saying, yes, I want to say use this to characterize minimizers. And what I'm saying is that, I mean, it's the same to say I want to have a given height. I mean, it's kind of an equivalent problem. So this is equivalent to keeping, let me write it first, length fixed, but maximizing area. Yeah, so what I'm claiming is that solving the previous problem where kind of like the total area is Z, but I want to minimize the length, it turns out at the end of the day, it's more or less equivalent to the opposite thing, where you keep the length fixed, but you maximize the area. And the question is, okay, what is the curve that for a fixed length bounds the biggest area? And the answer is it's the circle. So this is what you want to do. And therefore, this is what the proposition says. The proposition says subriemannian geodesics in R3 are exactly lifts of planar circular arcs in the plane. Yeah. Yeah, is that clear? So yeah, so at the end of the day, we're just looking at constant curvature curves in the plane, which is pretty cool. And now let's see what this says. So let's go back to the picture we had before. So here's P. Now here I draw psi of P. So these are the, let's say, so I'm at a point P and I want to study what are the geodesics that start at P. And what happens is that, okay, here are the possible directions. So these are directions. But we've said that for every direction starting at P, there's are many geodesics, right? There's the straight line, and then there's kind of like all the circles of different curvatures at P. Oops. So this means that for every direction that we have R many choices. So that means that the way that you should think about geodesics is that the geodesics are starting at P, they are parametrized by kind of psi times R, where this is kind of the curvature of the curve. And therefore, if I look, for instance, at the unit geodesics starting at P, they look like a cylinder, right? Because the unit is kind of just see this in psi. Yeah, so this is unit or vectors corresponding to unit geodesics, let's say. Okay. So I looked at this as already good, right? Because my space is 3-dimensional, and now I do have a 3-dimensional thing parameterized in geodesics, which is what you would expect. Okay, so hopefully that makes sense. And let me make a little remark, which is that basically what we just saw is that you can interpret this as a magnetic thing. So the geodesics in R3, we said they are like the circles of varying radii. And this is precisely the set of all geodesics that are like of all the magnetic geodesics in the plane, where their magnetic strength is some constant multiple of the standard area form. So if you know this, great. If you don't know this, then just ignore this comment. And a comment to be made is that this is general. So if you have any Riemannian manifold, and then you fix a 2 form, that is the magnetic strength, then you can always do the following construction. You can build an S1 bundle on top of M. That is the bundle whose curvature is omega. Now you can take a connection, and this will be your distribution. And you can live the metric kind of by pullback. And now what you will get is that the subriemannian geodesics in this bundle correspond exactly to all the magnetic geodesics whose strength is proportional to omega. Okay, cool. So let's move on. So what I wanted to do maybe with this picture, just to emphasize, is I wanted to tell you that this looks kind of like the Riemannian geometry, right? Like in Riemannian geometry, kind of geodesics at a point, starting at a point, are parametrized by the sphere, which is a super nice manifold. And okay, this manifold, this cylinder, I call this the unit cylinder sometimes, unit cylinder. This manifold is a bit worse, it's not compact, but it's still a nice manifold. But it turns out that, okay, one has to be a bit careful. So some pretty exotic things can happen in subriemannian geometry. So let me explain that. Right, so let me start by making, before I get to strange property number 1, let me make a comment. So let me go to the example in which we were. So this was R3. And here I'm drawing kind of, this is the plane XY, and this coordinate is Z. Okay. And now I'm going to draw for you the unit sphere, the unit ball in this space. And the unit ball roughly looks like this. It looks like an apple. So this is the unit ball in the previous case. And what you should note is that the points vertically over the origin, they are singular. So this means that the unit ball is not smooth. And in fact, this I learned from Marcello, actually, from a talk he gave. It turns out that in general, it's not even known if the unit ball is as smooth as a topological ball in a general subriemannian manifold. So that's kind of funky as hell, honestly. So okay, the unit ball can be super strange. Now, in this example, and this is exactly what Sander, was it, I think, asked. The question is kind of like, let's look at the geodesics here. So how do you get to this point? And the answer is that the geodesic looks a bit like this. And let me draw its projection. So its projection is the curve Sander wanted. Is the curve that does this. Is the curve that bounds area 1, because you want exactly to go up by 1. This is the optimal way of going. Now, what you can notice is that, if I want to bound area 1, I could equally just take a ball that has area 1/2, but then I do it twice. And what you can note is that this has bigger length. So this curve does something like this. Oops, I should, my pictures are bad. So what this says is that this curve is not a minimizer anymore. And you can keep doing this. You can do this for like more and more smaller balls. So this says any ball contains non-minimizing curves. And of course, in the Riemannian case, this never happens, right? In normal coordinates, the radii, are minimizers, non-minimizing curves. Okay, so this is pretty weird. So that means that the point 1 is in the cut locus. And now this is a strange property 1. So of course I could have chosen, instead of the unit ball, I could have chosen any smaller ball to reason like this. And that means that the cut locus runs all the way down to your point. So the point itself is in the closure of the cut locus. And this has to do, if you think about it, this has to do with the fact that I'm taking geodesics that are very inefficient because they loop a lot. So this means that this problem has to do with the fact that our unit geodesics, they were parameterized by a cylinder. Sort of as you go up in the cylinder, the geodesics get worse and worse. They're less They are not optimal as soon as you go a bit up. So non-compactness kind of is the problem of it. Okay, strange property number 1. Oh my God, we have 25 minutes left, so we have to hurry. Okay, so strange property number 2. So in the subriemannian setting, you can have geodesics doing like having funny limits. So what I mean by this is in the Riemannian setting, if you start at a point and you consider a sequence of geodesics starting at that point, so there will be a convergent subsequence to another geodesic also starting at that point, just because of compactness of the sphere. In this case, we don't have compactness because this cylinder is non-compact. So the question is the following. I'm going to take the unit geodesics. They are parameterized by the cylinder. And I'm going to take a sequence of geodesics gamma I, whose initial vectors, they get higher and higher in the cylinder. So these are geodesics that they have the same vector, but they have bigger curvature. And as such, what do we see? So this is R2, and vertically I'm putting R. So the whole thing is R3. So of course, the first one is just the line. Now the next one has a bit more curvature, so it's a big circle. And this is the projection. But of course, the lift of our big circle is a spiral that goes up. And now as you take higher and higher curvature, the projections are smaller and smaller circles. So their lifts are spirals that get closer and closer. So in the limit, what you see is that these things are kind of accumulating along against the vertical line. So this says something like this, kind of like, okay, so this is a general theorem actually. So maybe write this. So this is a theorem due to Colin de Verdier from like 3 weeks ago, or something like this. Trelat and Hilaret, Trelat. So this is 2020. So it says the following: if you have any contact manifold, so this is a manifold dimension 3, let's say, in this case, with a plane field of dimension 2, this bracket immediately at every point, contact, then subriemannian geodesics, a spiral around the reb. Okay, so let me maybe emphasize again. So what we see in this R3 case is that they spiral against the vertical. And it turns out that if you take any contact manifold, every contact manifold has like a bunch of like sort of canonical choices of dynamics transfers to the contact structure, transfers to the distribution. And what happens is that the subriemannian geodesics spiral along those, which is pretty amazing. And actually, I mean, I know from a contact topology point of view, this theorem is super intriguing somehow to try to understand what this means in terms of tightness over twistedness and things like this, if you know what that means. Okay, property number 3, and with this, it's the last thing before we get to billiards. So what can happen, so the geodesics we've seen so far are very well behaved, kind of, in the following sense. So if you're in the Riemannian setting, and you pick a geodesic, and now you take kind of the nearby geodesics, kind of starting from some point. So this means I'm looking at the vectors that are very close to my vector. Then what you will see is that at least for small times, the geodesic spray is super nice. So what I mean is that for small times, let's say the geodesic spray is submersive. So what I mean, right, is if I take the geodesics nearby, this geodesic kind of reaches this point, and the geodesics that are nearby, they kind of open up to form a ball around my geodesic. So this is cool. And the problem is that this is not true in the subriemannian case. So in the example we did, it is true. But in general, you can have the following thing, and it's not a property really just of geodesics, it's a general property of some curves are just bad in the presence of the distribution. So you can have a geodesic, for instance, such that you take the geodesic spray, so you take like nearby directions, and all of them will try to kind of pull into the same side. So somehow you'll have like maybe like a half space in a way. Okay, this is a very schematic picture, but you'll have sort of like a half space maybe where no geodesic arrives, because all the geodesics are being pulled by the distribution to be on one side. So that means kind of, for instance, here, this is, this you would call the wavefront. So that means that subriemannian wavefronts for a small time are nice. And what this says is that if you see this, the wavefront is probably terrible. And this can happen for arbitrarily small times. So actually, if you see something like this pooling phenomenon for some time, you must be seeing it for every smaller time. So in fact, geodesics are getting pulled immediately in one direction. So that means, for instance, that the wavefront can be super badly behaved for any time. Okay. Whew. Okay, so, oh my God, I didn't finish this. Okay, sorry. Okay, let's get to the point. So maybe just a comment is the following. Much like in Riemannian geometry, you do sort of geodesics are characterized in a variational manner, but this variational manner you can Hamiltonianize and pass to cotangent bundle. And what that means is that if you take the dual of the metric in the cotangent bundle, then its Hamiltonian flow is the cogeodesic flow. It turns out that the same is true in Riemannian geometry, sort of. So what we are saying is that you can take the metric in psi. This is a non-degenerate, a positive definite bilinear form. You pass it to the dual, and then you project the cotangent bundle to the dual. And this will define a function for you, a Hamiltonian function, the cotangent bundle. And what you can observe is that the kernel of this map is exactly the annihilator of the distribution. So this says that this function is invariant under the annihilator and is positive definite in a complement. And now let me do for you the picture. So here's the annihilator. And now what I'm saying is that the level sets of G star, they look like this. Yeah, I'm saying that the level sets of G star are cylinders. And this is exactly how we formalize what we saw before in the general case. They are sort of, you have like a positive definite kind of complement to the annihilator, and a non-annihilator, everything is constant. Whew. Okay. So this was a super rushed introduction to Riemannian geometry. I'm sorry. And maybe something that I should remark is that what is kind of missing from this picture are these like the bad geodesics, the geodesics that may have this pulling phenomenon. So the geodesics that you see in this picture in the positive level sets. So let me write it like this. So geodesics in cylinders are good, and they are like described in a Hamiltonian way. And then you have sort of geodesics that they live inside the annihilator, and these ones are the bad ones. And there's, I don't want to spend time with that, but let's just say that we focus on the geodesics that are nice, and therefore the story is very similar to the Riemannian one. Okay, and I should say that I should emphasize that understanding the bad geodesics is actually like maybe one of the biggest questions in Riemannian geometry. So I'm kind of like really throwing under the rug just a lot of stuff. But okay, let's do billiards. Whew, in 18 minutes. Let's see. So, so what is the point? So in classical billiards, the point is we've said that studying geodesics is a minimization problem. And it turns out that billiards are the natural minimization problem that is analogous to this, but with boundary. And what is the problem? You take the boundary and you ask yourself, what is the optimal way of going from a point P to a point Q, but if I'm forced to touch the boundary once? And what happens is that, of course, the answer is what you know. So what happens is that the optimal way is that you go here and you have an insiding angle. Here you have an outward angle. Let's say, well, I mean, this is in the planar case, and these two have to be the same. Okay, a way of formalizing this kind of better in the general case is that you take the inward tangent vector and you take the negative of the outward vector, and what you want is that their sum should be orthogonal to the boundary. This is the same. You just think about this, and in the planar case, this is exactly the condition with angles. So okay, so we've said, okay, normal geodesics, you can Hamiltonianize kind of the variational description of them. Now we have billiards, which are kind of the analogous thing, but with boundary, and now you can Hamiltonianize. And the answer is that basically what I just described, you can do the same with momenta. So basically, you have a boundary, you have an inward geodesic, and it reflects. And what you want basically is that this is a geodesic. Is there a question? Oh no, someone is entering the room. Okay. There's basically the way this happens is that this is minimizing, And the way in which kind of the inward and the outward are related is that you get the inward momentum, you take the negative of the outward momentum, and they have to annihilate the boundary when added up. So this is what it says: add the momentum, add the other momentum, they annihilate the boundary. Okay, so if you don't know this, maybe this was a bit fast, but kind of the punchline of this aims to be that in the subriemannian case, you do exactly the same. So you say, okay, now I want to study the minimization problem, but in the subriemannian setting. Again, this is some sort of variational problem, but with constraints. And I can pass it, and what I can do is I can just phrase it in the same way. What is the optimal way of going from P to Q with one reflection? And what happens is that the way in which this works is that you say, basically, I want to go from P to Q, and my momenta should add up to a thing that annihilates the boundary. So again, inward momenta minus outward momenta annihilates. Okay. So I will show you a picture now that will explain maybe what is going on. So the following, what we're saying is the following. I'm going to draw here TPM. Here I'm going to draw, let's say, M. And now M is a manifold with boundary. So this is the boundary. Now, here in TPM, as we said, we have our unit cylinder. And this is kind of where the dynamics of the geodesics live, of the subriemannian geodesics. And now what can happen is you have a trajectory here. Okay, let me show it like as follows. So here on top of the manifold, we have this cylinder bundle. So this I'm going to call the cylinder bundle over M. So this is CTM. Oh, sorry. Yeah, this is not the tangent bundle, right? I'm doing everything in the cotangent bundle. And what are we doing? So, okay, we have a trajectory here. This is just a good old geodesic. Now upstairs, this corresponds to some movement in the cylinder bundle. It has some Hamiltonian left. And now you reach the boundary and, well, the geodesic wants to escape. So what that means, let's say if I'm taking a point here, my P is along the boundary, here's P, then that means that I'm reaching some momentum here, let's say here. And now what do you do? This is the outward momentum. And now what do you do to determine the inward, like the next momentum? What you do is you say, okay, here is the annihilator of the boundary. This defines a line. So this is the annihilator of the boundary. And now, given the outward momentum, the inward momentum is the other path. And what is going on somehow is that if you, instead of taking the cylinder, you take the solid cylinder, and this I call DTM, then what you're doing is kind of adding to this orange hypersurface in cotangent space, you're cupping it off vertically. So what you're doing is you started with something that was a piecewise hypersurface with a Hamiltonian flow that stops because it reaches the boundary. And what you do, oh, sorry, I should use the same color coding. So you have this. And what you do is you add a vertical piece that completes it to a closed hypersurface in cotangent space that is now piecewise. And the billiard flow is just the piecewise Hamiltonian flow. Hopefully that made some sense. Are there any questions? So let me make a remark. So this is exactly the same construction as in Riemannian. So you do exactly the same to define billiards, and in, well, Finsler, semi-Riemannian. So in the Finsler and Riemannian cases, is I think classic. I don't even know who to attribute it to. In the semi-Riemannian cases, due to Khesin and Tabachnikov. So the idea in general is like if you have something that is like a bundle with boundary in cotangent space, what you want to do is kind of fill it in to make it into a closed object. Okay. So, okay, let's do the examples, which is actually the interesting part. So I want to go back to the example that we had, and I'm going to look at tables inside of this open manifold. So the easy table to look into is the disk inside the plane times R. Okay. So this table is super, I mean, okay, so yeah, so the cylinder is the boundary. It's it's where the reflections will happen. Now, what you can observe, as we said, is that both psi and g have a vertical symmetry. And due to Netter's principle, this means that the vertical symmetry must correspond to a conserved quantity, and you can check that the conserved quantity is the curvature. It's a computation, or just think about it for a while, and you'll see that it's true. And what we're saying kind of is like, since the boundary is vertically invariant, it interacts nicely with the symmetry and therefore nicely with the conserved quantity. So that means that the curvature is conserved upon reflections. So what this is kind of saying is that basically is the following. Well, okay, I will do it in the next slide. So maybe let's not do it now. So what we're saying is, since the curvature is preserved on reflections, then this means that what we're all doing is just looking at magnetic geodesics in the disk itself. Yeah, just like the geodesics in R3, where magnetic geodesics in the plane, that is like circles of various curvatures. Since the curvature is preserved upon reflection, this corresponds to magnetic geodesics. And again, this is general. So if you have like a manifold with boundary that has a G and a magnetic two form, then you can do the same. So let me do the full pictures, let's say. So what we're saying is the following. Here I have my table. Well, here I have D2. So I'm gonna just work in the projection all the time because it's easier. What we're saying is, if I have a trajectory, okay, I'm gonna draw 3 legs because otherwise it's too much. Then what you see is that, of course, the insiding angles are the same. Then this is a conserved quantity, so this is alpha upon all further reflections. Then also the radius is preserved. So this is, if this is r, then this is also r. And this means that we have 2 integrals of motion apart from the Hamiltonian itself. So that means that this is completely integrable. Okay. Now the next picture, okay, I'm gonna do the next picture like this. Then you can also notice that because of the symmetry of the problem, I mean, due to integrability, essentially, there's a unique, given such a trajectory, there's a unique cylinder such that you touch it once in between reflections. This is called a caustic. And what we are saying is that basically all geodesics satisfy this, all of them have a corresponding caustic, and all the cylinders will be caustics. So the claim is, yeah, the table is foliated by caustics. This is again integrability. Then, okay, there's no periodic orbits inside the table. This is clear because if I'm in D2, we said that the projection of a geodesic that does not reflect is just a circle. So when I lift up, this is a spiral. So, okay, no closed orbits. Another question is, what are the periodic orbits? And the point is that you can give the following characterization, and let me give you just the answer. So the answer is, since I know I want to do K reflections, I know that my reflections must form a K-gon. This K-gon is ordered. So for instance, this is the first, and then maybe this is the second, then this is third, fourth, and fifth. So I'm forming like a star. I mean, you don't have to go through the vertices in order, of course. You can go in any order. Well, in an order that is periodic. And now what you can observe is the following. So let me maybe do the following drawing. So let's take, for instance, the trajectory that has no curvature. So this is really a star. And now the question is this closed upstairs? And the answer, as we saw before, I mean, this is certainly closed in the projection, but is it closed when I lift? And the answer is, it should bound area 0. And does it bound area 0? And the answer is no. Because you can take the origin and you can do the following check. You can observe that this area is positive. And what this says is that as you travel from 2 to 3, 3 is higher. And this is true in every leg I do because of symmetry. So in fact, you just go up. So the point is, okay, then where are the periodic orbits? And the periodic orbits are here. And now this is hard to draw, but the answer is that there's a unique circular arc. There's a unique curvature. So given any star, there's a unique curvature that makes the following true. The area that you leave in this part, in this little triangle, is the same as the area that you leave in these 2 legs. Okay, so there's like 3 parts. These two have the same sign, and the gray part has different sign. And there's a unique curvature that realizes this. So this says, yeah, there exists unique curvature for each n-gon, and or let's say a star, such that corresponding geodesic closes. Okay, so this is an exercise you can try to do. Think about it. It's kind of funny because it's like nice drawings you do in planar geometry. But what all this says, of course, is that since the table was integrable, I can give you all the periodic orbits. This is the baby example. What is kind of more interesting is that what we don't know is if there's other tables that are completely integrable. And we conjecture that there's none. And the observation for why this probably should be true is that in magnetic, so maybe let me write it like this, observation, ellipsoids in R2 are not integrable for most magnetic strengths. So what this says is the ellipsoid is kind of like the next example you would try to look into for integrability. And for normal planar geometry, it is integrable. But once you introduce a magnetic term, for most magnetic terms, it's not. And we've seen that this subriemannian case includes all curvatures. So that means that for most curvatures, you won't get integrability. Okay, but yeah, we don't have a proof of this. Maybe the proof is completely easy, but we didn't try very hard. So maybe that's something to be done. Okay, and let me get to the coolest punchline, I think, of the talk in the last 4 minutes. So,
by the way, you don't have to stress out so much. If you
I'm
need
very
5 more
stressed
minutes, that's fine. Don't worry. I didn't want to say anything before because it was fun to see that you were realizing the diamond was like getting shocked, but don't worry about that. Take the 5 minutes.
Okay, I will try to give this punchline and finish. Okay, so what I want to say is, yeah, so we saw before, right, that if you have a sequence of subriemannian geodesics, then what can happen is that if their curvature becomes unbounded, so if they go like away in the cylinder, then they will kind of spiral, and their limit could be something strange. In the contact case, it's just the rate flow. So the question is, what is this in billiards? So, okay, let's make the 2 silly cases first. So, okay, if there's no accumulation of reflections, so this is basically a non-billiard phenomenon in a way. So if reflections don't accumulate and curvature is bounded, then you just get a billiard thing. Okay. If reflections do not accumulate, but the curvature explodes, then that means that you're kind of getting a sequence with like really tiny curvature. So you get a spiral, and therefore things converge to the rate. So, but okay, what happens in the billiard? Like when reflections actually do happen more. And there's sort of 2 setups. Maybe I will try to discuss both. And for this, I need to introduce tiny notation. So here's my table once again. This is d2 times r. And what you can observe is that the boundary of the table has a foliation. What is this foliation? The foliation is given by, you take the tangent of the boundary and you intersect it with psi. You call this the characteristic foliation. Let's define here. And what we see, of course, what is this characteristic foliation? So we saw that the contact structure turns from the origin to a slope 1 in this case, because the disk has radius 1. So that means that this foliation is just the foliation by lines of the slope 1. So this is a slope 1. And now, kind of like a stupid remark, is that the boundary, together with this foliation, and with G restricted to the boundary, this is not really subriemannian, right? Because this is a foliation. But okay, it's something. It's a distribution with a metric. And kind of tautologically speaking, by definition, these things are geodesics. So this is called, I call this a boundary geodesic. Kind of tautologically, it's the optimal way of traveling within your leaf. So what is the punchline? If reflections do accumulate, but the curvature is bounded, then your limit will be a boundary geodesic. So yeah, one of these leaves. And the picture roughly looks like this. You just kind of get reflections that are getting like a smaller angle. They get more tangent and they follow this orange thing. Okay. However, something more interesting can happen, which is what is the analog of the rape phenomenon, but for the boundary, which is that, for instance, of course, you could have a trajectory that is a cylinder that is tangent to the boundary, but it doesn't reflect. It just kind of passes through it. Plop, 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 plop. So this would tend to a rape orbit that is along the boundary. So this has like, it's a curve of slope infinity in the boundary. Yeah, sorry, I'm finishing. And then let me give you the last exotic case. Maybe not, I'm running out of colors here though. So the point is that you can in fact realize any slope. So the point is, if you do some sort of like clever thing, when you combine how big your circles are and how apart there's 1% slope. And this is really weird. This is kind of extremely remarkable, I think, because what are these curves? I mean, like we are getting some sort of canonical dynamics in the boundary associated to the billiard problem, and it's not very clear what these are. And certainly, I mean, they have nothing to do with this, and it's not clear to me what they have to do with the distance in R3 restricted to the boundary. So the big open question somehow out of this is, we understand this in this example, but what is the nature of these creeping orbits? What are these limit orbits we get at the boundary? What do they mean? Kind of in a subriemannian fashion. And okay, let me give you like a last picture, and with this I finish. So kind of like the last comment to be made was that now we can consider tables where the boundary is wrong, is worse. For instance, it can be worse in the sense that, in this case, you can take a boundary that has a tangency with respect to the structure. So here at the origin of the plane, the boundary of the table and the distribution are tangent. And this means that if you look at the characteristic foliation, you're getting a singular foliation that in this case is radial. So let me just do a picture, and with this I finish. So what we kind of proved in this example that is kind of funny is that you can find a sequence of geodesics that they come really close to here. So they're approaching the line, a half line, and upon reflection, they spiral up. So you can get kind of like, it's kind of stupid. So in C1, these things converge to a half line, but said theoretically, they converge to something that is doing this. Boop. And the big question for us, I think, on this example is that you can observe the following, and this is observation that was in a paper of, let's see, Canarsa, Barilari, Boscain, and I think Karen Haberman, which is also here. And what they observed is the following: if you think about the metric in the boundary, in the sense that you take the boundary, the characteristic distribution on the metric, then this is actually points have finite length, because there's like a way you can be here, you travel along this boundary, geodesic to the center, and then you go through other thing. So the question that we have is, can you find a sequence of billiard trajectories that they converge to this? Like, kind of piecewise geodesic appear as a limit? Are these limits? Okay, so I think I had some more questions, but I think I will stop there. And yeah, thanks a lot for listening. I'm sorry I went over time.
Don't be, that was very, very interesting and clear. Thank you very much.
Yeah, thanks.
So yeah, let me add a virtual clap and a real one.
Thanks.
Does anybody have questions or comments? Again, feel free to use the chat if you don't want to be recorded or live streamed. Otherwise, you can just unmute yourself.
May I ask a question? So very nice talk, by the way. So I have a question. I'm not completely sure how to phrase it, but so in classical billiards, you have that the length of periodic orbits can be related to the eigenvalues of the Laplacian.
Right, yeah, that spectrum question.
The actions of these orbits you found, for example, in the Heisenberg group, in the billiard.
All right, so that would be very interesting. This I don't know, but it should be related to some like yeah, like the hypoleptic Laplacian in the table with some natural boundary conditions, something like this. Yeah. That should definitely be true. Maybe a comment to be made also about this question, because I think it's interesting, is that it seems, I mean, I'm definitely not an expert on this. I think there's some people in the audience that probably can maybe say more. So what we've seen of this, like some trajectories being limits of geodesics, that means that there's some things that are not billiard trajectories anymore, but they still appear. And this should have also a counterpart in the world of the spectrum of the sub-Laplacian. So you should see kind of like Raybour bits pop up, like Raybour spectrum pop up, maybe, or like see like this, like we commented also these weird geodesics that are not Hamiltonian in this manner. Their spectrum should also pop up, maybe. But that I don't know very well. I think maybe Marcello, maybe he can say more. I don't know.
Thank you.
So,
no, thanks, Alfonso.
Any other comment or question? If not, I actually have a few here listed.
Sure.
So, I wanted to ask you one. Well, first I start with the dumb question. I don't know if it's ready or not, but in the contact case, since you have the relation between the trajectories and the motion of a particle in a constant charge particle in constant magnetic field, do you know if these trajectories that travel through along the boundary are related, for example, to topological edge states, this kind of trajectory that are somewhat stable and remain close to the boundary and keep bouncing around?
Oh, but that's what I would call this gliding phenomenon, right? That is exactly that, I'd say. Yeah, I mean, so I don't know, like the name you said, I don't know what the name is, but what you described, the answer is yes.
And the other thing is, how much of what you find do you think is related to the fact that you're using a constant structure here? And how much do you think is going to appear or will be different if you use look at different structure or different, even widely different, like take Martinet or something that is non-equiregular, more or less singular, or higher order step Carnot groups, things like that.
So, okay, but still in the Carnot groups. I mean, so I think in the Carnot group case, if you put like left invariant stuff, you should still be able to do quite a similar theory. All right. That is my impression. What is that? But then, of course, then the question would be, yeah. So I mean, I would say like in the Carnot case with left invariance, probably similar things will happen, although that's to be understood. Then, for instance, things that are interesting, I think, and should be true in the general case are, for instance, this gliding phenomenon along the boundary. So you have things that, like, so that billiard trajectories, maybe let me write that. So billiard trajectories with bounded curvature tend to boundary geodesics. I think this should be true in general, for instance. And the idea kind of is like, for instance, and it should be even true that every boundary geodesic is a limit. So for instance, in planar billiards, this is not true, because for instance, if you have concavity, then it's pretty clear that no billiard trajectory can approximate this, because due to concavity, you just go away. However, in magnetic billiards, the notion of convexity or concavity is different, right? Because you want to be convex with respect to the curvature. And in our case, because you have every curvature, then it seems that there's always convexity, I think. So for instance, this thing should be general. I think there should be like, I mean, along the lines of what Alfonso was saying, I think there should be quite general statements about spectrum, but I think this is a very hot topic. Of course.
But hitting the tangential section looks like it could play the trick of the concavity, right? It's like those trajectories that you were showing that get close and then are killed.
Yeah. So that is so that we don't understand yet. So that type of phenomenon, we just don't know exactly. It could be something like that. I do agree. Yeah, what should I say? Yeah, that's definitely true. I mean, for instance, I think something that is an interesting question. I think I wrote it somewhere. I don't know. It would be like, for instance, how do you determine the nature of the singularities of the boundary of the table in terms of the billiard reflection? So that seems a very not general question, and it seems that, I mean, you should not try to tackle it for like particular metrics, but just as a general thing. I don't know. Yeah, sorry, Marshall. I think I rambled. I know that's an answer. Yeah, no worries.
Are there other comments or questions? If not, then let me thank you again and clap.
Yeah, thanks.